Some examples over 5.2 material where we are looking at what we call exponential functions, right? And that study does start off with a very fundamental form for exponential functions. And as you work through some of the examples, you do see that form does grow in complexity, and that growth in complexity really is it breaks down to an interpretation that happens in that idea of transformations, right? We can take these very simple forms of exponential functions that we're going to see initially in our study and be able to apply the idea of transformations to these functions to develop these more complex functional descriptions, right? That we encounter and that we have to learn to analyze, right? So here we start off with these two basic exponential functions. And if you remember, an exponential function is just a function in the form f of x equals b raised to the x power, right? Where when we think about the value of b is the base, right? It is what we call the base of the exponential, right? And that b value can be any real number except for the value of 1, right, in an exponential function, in order to exhibit what we call exponential behavior, right? And what does it mean to exhibit exponential behavior? Well, we could see that if we spend a little time looking at maybe some of the tables and graphs of some very basic exponential functions. If you notice, these two functions up here, f and g, fit this generic description. In this particular case, our value for b is equal to 4, and in this particular case, our value for b is equal to 1/4 in value. All right? And with those functional descriptions, right, of exponential behavior given by 4 to the x and 1/4 to the x, we can analyze that behavior perhaps first looking at a table of values. Right? And if you spend some time in the notes, right, you will come to find that there are 3 coordinates that are always easy to find when looking at any exponential value, any exponential function. And that comes, any exponential function in this generic form, f of x equals b to the x, right? Those come from these 3 cases we see in the table. The cases for when x is equal to 0, the case for when x equals 1, and the case for when x equals -1 in value. And what we had said in general, right, for this exponential function b to the x back in the notes, was that at the value of 0, b to the x will always be b to the 0 power. And any number to the 0 power, right, always results in the value of 1 in value. So regardless of the simple exponential function, whether it's the function f of x where we have 4 to the x, or whether it's the function g of x where we have b equal to 1/4, right, even when I plug 0 into g of x, I also get the value of 1 as a value found in the table corresponding to the input, the independent variable of 0, right? 0, 1 is on the graph of every exponential function that fits this form. That very specific location is on this graph for every generic form of an exponential given by this form here. All right? As for the other points we point out, is if I was to make the x value 1 up here, if I was to consider the case for x equal to 1 in either case, that will always correspond to the coordinate, what am I doing? 1, b in value, right? Whatever happens to be the base for this function f of x, that would be 4, would be what we would have happen at an x value of 1. And at the case for g of x, whatever our base is, that being the base of 1/4, that would be the value of x, or at g of x that we would see. That would be the output value when we input the value of 1 into our function. Right? In any generic case in the form b to the x power, right, when that x value is the value of 1, right, the result will always be the value of b for the output of that function. As for the value of -1 then, when we put -1 into the function b to the x, what happens is we do get back the value, right? If we think about b to the negative first power, right? Well, you have to understand that that negative power, back to our power rules, is equivalent to 1 over b to the positive 1 power. We can make that negative power into a positive by reciprocating the ratio, moving, in a sense, this power of b in the numerator to the denominator, right? That will produce this result here, where you will now see just b to the first power. Well, that's just b. So this leaves us with 1 over b, right? So here, when x is equal to -1, the result will always be just 1 over whatever our b value is. In the case of f, our b value is 4, so that is just simply 1/4. In the case of g of x, now this is where it gets a little tricky, our b value is 1/4. So if I think about what's going to go in here, it's going to be 1 over 1/4 in value, where dividing by this fraction is actually the same as multiplying by its reciprocal. Take the numerator multiplied by its reciprocal, flip it over, and that really just becomes 1 times 4, right? Which equals just 4 in value. This results in 4. And notice what you see happening here, folks. All right? You see a little bit of this reciprocal behavior happening between these two functions f and g with respect to them being these exponential functions where their b's, if you notice, their b values are really just reciprocals of each other. Right? If we continue filling in this table then, right, we might say then in the case of f being 4 to the x, what would be our output if x is 2 in value? If I have 4 to the second power, right? Well, recall 4 to the second power is equal to 16 in value. And if I consider that value at 4 to the third in power, that would be equal to 64 in value. If I was to continue in the negative direction and consider my case for x equal to -2, right, that would be 4 to the negative second power, which if we follow the rules that we followed over here, this would be 1 over 4 squared, which does end up equaling in the end 1 over 16 in value, right? This tabled value would be 1/16 in value, right? Now, if I was to work the table similarly with respect to this being our function and this being our value of b, right? In the case for g of x, the value of 1/4, if I raise that to the second power, that power will distribute to the numerator and denominator. That will become 1 squared over 4 squared, which does become 1 over 16 in value. All right? Again, you notice a bit of that reciprocal relationship happening here with these values. When x is 2 in this case, we get 1/16 in value. Similarly, if I make x 3, you could maybe expect what's going to happen there. I will get 1 over 4 cubed. That would be equal to 1/64 in value. All right? If I was to head in the negative direction, as we had seen here with -1, this is going to flip over this base and then apply the power. So 1/4 reciprocal is 4, and then this would be in a sense 4 squared, which would just be 16. Right? We could see all this also given in our calculator. Right, let me go look for my calculator here. Bring this over. See if we can get that into view here on our calculator. Let me reset my memory on the calculator. Just because I was using this to do some advanced work the other day. I don't want to let that interfere here. So let me reset my memory. Remember how we're going to use our tables. We're going to go over to y equals. And we could perhaps put in these two functions. If I want to put in 4 to the x, that is 4. And then I would use my caret, the upper wedge, the wedge key here. This arrow that's pointing upward. And raise that to the power of x. That gives me the function 4 raised to the x power. If I was to look at 1/4 then, we could do 1 divided by 4 inside parentheses and raise that to the x power. That is 1/4, that base of 1/4 raised to the x power. And I do write it out this way to make sure that the calculator is recognizing that the entire base is the value of 1/4. All right. If we were to look at our table then, that's the blue command above the graph button, right? So if we hit second graph, we will produce our table of values here. All right? We can see it's 0, it's 1, 4, 16, 64, 256 for the case of f of x here, right? We can see those values beginning here. If we were to head up into the negative direction on our table, can we do that? Yes, we have to go over to the x column and scroll up, right? At -1, we are 0.25, which corresponds to 1/4 in value as a fraction. 0.0625, that is 1/16 in value as a fraction, right? If we notice what's given over here in table for y2, right? A little bit of glare, right? If we notice what's given over here in the table for y2, right? When x is -2 in value, we are the value is 16. When it's -1, we are 4 in value, right? When we are 0, it's 1. And when we are the value of 1, we turn into 1/4. And at 2, we are 1/16. And at 3, we're 1/64 in value. That is 1/64 as a decimal value, folks. All right? We get the corresponding tables, right? We can do all that on our calculator. And we can see what we could think of as that exponential behavior, right? In the case for f of x up here, you'll notice in the table the exponential behavior, right, is illustrated as we make our x values increase in value. As x gets bigger, notice our y values start to grow exponentially, where we are starting to get some scientific notation being expressed here. This is 1.05 times 10 to the 6th power, which is getting to be pretty large, right? And it does get larger quite quickly, right? Whereas, if you notice what's happening over in g of x as x increases, we are seeing more scientific notation, but this is for very small decimals. What's happening in our exponential function here is actually what we call a decay. This function illustrates g of x is illustrating exponential decay, whereas function f of x is illustrating exponential growth, right? Growth illustrates the values of x, or the values of your outputs growing exponentially, whereas in exponential decay, it's illustrating the outputs of your function decreasing exponentially, decreasing in this basic form towards the value of 0. All right? If we head in the other direction here, I got to go back over to x to scroll up. Right? We can see what happens in the negative direction. Right? We do see that the exponential function illustrating growth, if we head in the negative direction, actually illustrates decay in the negative direction. Whereas the exponential decaying function, the one where b equals 1/4, is actually illustrating exponential growth, right? We see those extremely large values given by that scientific notation there, right? If we were to look at these graphs, right? Remember, the way we get over to graph is we just hit the graph button, right? There's one of our graphs. Let's see if we get the other one to sketch in here. There's our other graph. And it does graph them in order. So the first graph we saw is the one illustrating growth. Actually, we could isolate that, go over here, hit enter. All I did was hit enter while highlighting that equal sign, and that will turn a graph on or off. So let's turn off the decaying graph. All right, and that'll be our graph illustrating growth. What we will notice is that none of that graph is down here below the x-axis, right? In fact, if we were to set our window settings and zoom in, we would be fine from zooming in and looking at just the upper half of this graph. None of this graph dips here below the x-axis. In fact, we could even bring our window down some. Maybe we make our y max the value of 4. Right? And we'd even have to probably zoom in a little closer to see that. So maybe we bring that down to 1. Not 1. We'll bring this down to 1. And then let's zoom in this direction now, too. Let's go from maybe negative 2 to 2 there and see what's happening in our graph. Yeah, we can see that is starting to be our illustration there. If I was just to maybe shift the x to the left a little bit just to see what happens as we head maybe in that direction. Well, let's keep that at +1 so we at least get the x-axis in there. All right. You can kind of see what's happening in our graph there, right? As we head to the left, we are running along top of the x-axis in this graph. There really are no negative exponential values. And you may have seen that in the table. None of these outputs were negative in value, right? That x-axis is playing the role of a horizontal asymptote, where in the exponential function, it is describing this this end behavior that occurs on the far left end, right? If we were to look at the case for decay, and that was to go and turn that graph on and turn the other graph off, and then adjust our window settings to maybe go from -1 up to 4 in the similar looking picture, right? There is our illustration of exponential decay, right? We are starting at a really large number and getting rather small pretty quickly with respect to x. And we never get smaller than 0. In fact, you never actually even reach 0. You get infinitesimally close to 0, as close as you could imagine being to 0, right? But never actually reaching the value of 0. Again, the x-axis is playing the role of a horizontal asymptote, describing that end behavior way over here on the far right side of the graph. All right? That is what we see when I'll go back to just a standard zoom. All right? That is what we see in this graph of just the decaying exponential function itself. They never dip below the x-axis. They run along the top. And maybe we even just make that obvious when we graph the two back together. Let me go turn this one on. All right, here's going to be the growth function, and here's the exponential decay coming along. There it goes, right? So those are the two graphs sketched side by side, right? Or graphed accurately side by side on our calculator. If we wanted to actually lay out those sketches alone here, what we rely on, folks, is just really this information. This information, along with understanding that in these sketches, both of these sketches, the x-axis plays the role of a horizontal asymptote. And in the case for the growth function, we are going to describe the far left end, right, with that horizontal asymptote. And with the decay function, we're going to be describing the end behavior on the far right end. Right? In the exponential growth, the right end of the graph will point up, whereas in the exponential decay, it'll be the left end of the graph ending pointing up. And what points do we pass through? Well, it's these three common points. 0, 1 will be on both graphs, as well as the location 1b and -1, 1 over b. All right, so we're going to maybe want to produce a sketch that falls between those values. So let's go with 1, 2, 3, 4, right? So we know we pass through here, here, and here in our sketch. With this describing our far left behavior, our graph would run along the x-axis and then pass up through those 3 points, heading up towards positive infinity as x increases towards infinity. All right? This again being your x-axis, this being your y-axis. In this graph, right, we would see these points coming into play in our graph. So 1, 2, 3, 4 units up my x-axis. But the location, the height of 4 will occur at -1. So -1, 1, and 4. Right? Would occur up here. And the location of 0, 1 would not change, but the location occurring at 1 would actually be down here at an output of 1/4. The graph having to end way over here, and as it comes back through and passes through those points, heads up towards positive infinity as x heads back towards negative infinity. Right? We see that illustration for those graphs, folks. Right? So to begin with, that's what we're studying here with exponential functions. And this is just two introductory examples here, or a couple introductory examples of tabling and graphing to help us start to understand what we mean by exponential behavior, right? Or what it means to be exponential behavior in a fundamental form, right? And that value of b, that value of the base, plays a big role, right, in beginning the values of a table and understanding that behavior, as well as when it comes time for graphing, right? Along with understanding that when you look at the output values over here, they're never going to be smaller than 0 in this fundamental case, right? And that in the case of growth, when b is greater than 1, notice that's when you have growth here as b is greater than 1, right? And decay occurs when b is less than 1. And with respect to limitations on b, again, what I really should have said is b is going to have to be bigger than 0, and b is not allowed to equal the value of 1. Right? So it's always going to be somewhere between 0 and infinity, except the value of 1. When it's bigger than 1, you have growth, and when it's between 0 and 1, you have the case for decay. All right? This is exponential growth. This is illustrating exponential decay. All right? So, folks, that's my first bit of video here. I'll be back with a couple more cases where we're going to look at some advanced graphing here. Right? Looking at some advanced analysis. And all this we're going to see is based upon transformations applied back to some fundamental cases. Right? So I will see you then. Hey there, college algebra folks, back here with some more examples of working with exponential functions, where we're going to go through a little advanced analysis of functions, exponential functions. What we should be doing to begin with here is, well, first of all, what we take note on is we are going to look at some problems here where we're going to be graphing, right, some exponential functions that kind of resemble functions that we've seen, some of these basic functions here, right? F of x equals b to the x, but they are certainly a bit more complex in their their setup, right, in their form. Where what we see happening here and what we should be, in a sense, doing is we should be adding 2 more functions to our library of functions, right? Well, be careful there. We should be adding, right now, 1 more function type to our library of functions. We're going to add a second one in just a section of material. Next section, we'll add 1 more. But in this section, what we should be adding to our library of functions is this fundamental description, right, of an exponential function. Right? This b to the x description that we saw in our previous example, where fundamentally we should add to the graph, right? If we think about what graph relates to this function back in our library, it's going to look something like this, where you will certainly still see those coordinates 0, 1, right, on each graph. But when you go to interpret these other points, you will have a point at 1, comma b in both cases. And you will have a coordinate at the coordinate negative 1, comma 1 over b. In both cases, right? And just depending on what b's behavior is, you will have a case for either exponential growth or exponential decay back here in your library. Remember, and along with that, you'll also add those horizontal asymptotes to that understanding that is happening here functionally. Right? This fundamental understanding of exponential behavior. All right? You want to add this to your library so that when you see a more advanced case where this requires a little bit more analysis than what we saw fundamentally, right, you'll be able to start tackling this analysis. And what we really ought to note here is really what we have going on is just transformations. Right? Here we're going to have transformations applied to, in this case, that fundamental function f of x equals 4 to the x power. Right? This fundamental function here back in our library. And we know what that looks like, right? We worked through that example here. Right? Where all we're going to do is transform this graph now using a bit of transformations. And remember how those transformations are interpreted? I believe this is given back in the notes, right? In terms of the transformations, you might say here we have is g of x could be interpreted as a quantity big A times your base of little b raised to the power of big Bx plus c, all added to a big D. Right, a capital D, where the little base b is the base little b back here in your functional understanding, right? Here you might say this is f of x equals b to the x, right? That's little b, and a, b, c, and d are all transformational descriptions, right? A, b, c, and d are just descriptions of transformations. And back here, right, we could start to align this with this form. If we said this is a times little b raised to the power of capital B times x plus c, all added to capital D, you could start to make some alignments to what are the values of a, b, c, and d. Here you might notice you're not really multiplying anything in front of the 4, in front of the base. What you're really multiplying by is just the number 1, right? In this case, a is just 1. This is that all times 1, which really is no change, right? So we don't show the value of 1. As for b, it's this number in front of x in the power. We don't have a number in front of x in front of the power, so that's because it's also the value of 1 being multiplied by that x. As for c, it's what we add on to that quantity up there in the power, and that is 5. And as for d, it is what we add on to the entire quantity here at the end, and that is minus 7 in value. Well, you want to remember this describes vertical compression, stretch, or reflection, right? this describes horizontal situations of compression, stretching, or reflecting, right? C, right, you want to remember, you're going to use C divided by B, right? And that is going to describe some horizontal shifting, right? And D alone is going to describe some vertical shifting, up or down, so many units, right? So if we put that together here, right, all we're really doing is shifting. Now remember, we interpret this as the opposite. If B is 1, C over B is just going to be C. So C tells us because it's positive, we shift left 5 units. And here, because D is negative, we're going to shift down 7 units. And what is going to shift are the points seen here in this graph, where it's going to be these coordinates given here. Right? And if you remember how we do that, we take the x values of these coordinates here, and we subtract our value C over B from them, right? After multiplying them by 1 over B, right? Now 1 over B is just 1, so we really don't worry about that, and we just subtract the 5 from each of those. And then we add negative 7 to all, well, yeah, we add negative 7, which is like subtracting 7 from all of these y coordinates back here in our graph. And what this is going to cause is this whole graph right here to shift left 5 units and shift down 7 units. And along with that shifting left 5 and down 7 for the graph, that will also happen to this asymptote. And that's usually where I start in my graph, as I will note, because we're going to shift left and down 7, my asymptote is also going to shift down that 7 units. So my horizontal asymptote in this graph, right, that used to run along the x-axis, that's going to describe the end behavior here for the left end, because I don't have any reflecting occurring, and we're describing exponential growth, and that was what described the left end here, right, is going to start here, and then I'm going to pass through some points. Now how, again, I'm going to find those points is the whole graph is shifting 1, 2, 3, 4, 5 units to the left, right? If we almost imagine that x-axis shifting, that would be this axis right here, right? And if I need to, I can always look at my table of values. I'm going to take, let me bring in a blank sheet of paper here, just to kind of highlight this. Remember, what we can do is we can take the coordinates from xf of x, which were negative 1, 1 over b, in this case 1/4, 0, 1, and 1 comma 4, and we can convert those into now coordinates in g of x, right? We're just going to subtract 5 from each of these. Take away 5, right? So this would be at minus 6, this would be at minus 5, this would be at minus 4. No. Yeah, minus 4 in value, right? Working with this 1 here, right? Whereas with the y coordinates seen here, how I'm going to get those over to y coordinates over here is I'm going to actually subtract the 7 from those values, right? I'm going to add this number, which is like subtracting 7. So 4 minus 7 is negative 3. 1 minus 7 is negative 6. And 1/4 minus 7, right, is negative 6 and 3/4 in value, right? So if I put those locations into my graph here, right, negative 4, negative 3, here's negative 3, here's negative 4, would be located right there on my graph, right? Negative 5, negative 6, here's negative 5, where my x-axis would have also moved to if it moved. Negative 6 would be right here on my graph. And then the location negative 6 and negative 6 3/4. Here's negative 6. Negative 6 3/4 is really close to that asymptote. It's right there on my graph. So now if I know my graph is going to end down here and pass through those 3 points and illustrate exponential growth, there is my exponential function. Right? That is what it looks like. Right? We can do the same thing down here. Right? Doing the same thing down here, right? We can look for our values of A, B, C, and D. Right? We can note that we are comparing back to f of x equals 1/3 raised to the x power. There's my exponential function. Right? My fundamental function, where all I'm doing to it is what? Multiplying it by 10 and subtracting 5. Right? There is nothing happening to the x. In a sense, b is 1 and c is 0. A is the value of 10. D is minus 5 in value. Right? And what we're going to shift around, folks, what we're going to shift around is this graph f of x. Right? If we think about the graph of f of x, it's going to illustrate exponential decay, which will look like this. Right? X-axis being this horizontal asymptote, and it's going to pass through a couple of quick and easy to find points. Those points being -1, 3, 0, 1, 1, and 1/3 in value, where we're going to translate those over into coordinates that would be on the graph of g of x. We're going to take each of these x coordinates and do nothing to them, right? Technically, we would divide by 1 and then add 0 over 1, which is not going to change those at all. But it's the y coordinates that are going to change with a and d. You just multiply by this and then add on this. So 10 times -1 is -10. Minus 5 is -15. All right? 1 times 10. Let me back up. I just realized what I did wrong there. Can you see what I did? I didn't multiply 3. It's 3 times 10. This y coordinate, that's 30. And then we subtract 5, that's 25 in value. So be cautious with that. That's positive 25. It's then this one is times by 10. That's 10. And we subtract 5 from that, and we get 5 in value. Right? And then 1/3 we'd multiply by 10. That is 10/3. Right? I have to keep track of that. That would be 10/3 minus 5. Well, that would be like minusing 15/3 if we did a common denominator, which would leave us with -5/3 in value. So this would be at -5/3 in value, or that's what? About -1 2/3 in value. All right? So these would become the coordinates on the graph I'm going to transform. And what we can note happening is this is a vertical stretch by a factor of 10. This is a shift down 5 units. So we do have to kind of sketch this in here. The highest we're going to go along the y-axis is up to 25, plus 25. So maybe we do this by 5s. 5, 10, 15, 20, 25. Right? And then we're going to go down 5, and that actually would be where our horizontal asymptote would be at in this graph. And then if we start to scale in these points, -1, 25, here's -1, that would be right there on my graph. So let me actually move that 25 to the other side. This is -5, right? And that would be a point on my graph, right? We're going to pass through the coordinate 0, 5. That would be this point on my graph, right? And we're going to pass through the coordinate 1 and -1 2/3, right? -1 2/3, well, that's pretty close to the x-axis there, right? If this is down here at -5. Where we do note what the horizontal asymptote is indicating is this right end behavior here, folks. Right? And if we go backwards from the right end behavior passing through those coordinates, that would be a sketch of my graph. Right? That would illustrate the graph of that transformed function. All right, so that is sketching, right? That is sketching. That is doing a bit of an advanced analysis with exponential functions. What we're essentially doing here is adding another function to our library, this fundamental function f of x equals b to the x, where we do have a kind of a fundamental understanding of what those functions would look like if we had the case for growth or decay. And then based upon our fundamental understanding, we can apply those fundamental understandings to more complex scenarios, right, by using the idea of transformations. And then don't forget, folks, you can always double check your answers here, right, in the calculator, right? Let's go ahead, first of all, put it back to let's go with a standard zoom here. Well, that's going to sketch out our old graphs. I can pause that. We'll go underneath here, and notice our first function is just the 4 to the x function. So I could say instead of 4 to the x, let's make that x plus 5, and then we'll subtract 7 from it. Let's turn off this graph. Let's actually just delete that one away. All right, and if we hit graph now, yep, we see that picture come into play, right? And that all fits within the window quite nicely, so we don't have to adjust much to see that graph. Right? Apparently we do have that horizontal asymptote at where? Well, at -7. Right? And where would be some key locations on this graph? Well, we see them over here, and we could probably see them also over on the table for this function. Right? Notice its orientation and shape in that space is very similar to what we see here. Right? With proper end behavior. Right? As for g of x, right, we might go underneath our y equals menu. This number, our base changes, so let's just clear this out. Let's start fresh. This would be 2 times the quantity 1 divided by 3. That's going to be raised to the power of just x, and then we'll subtract 5 from that. Oh, and then notice I put a minus in there for some reason. That should be a multiply. All right? If we hit graph, we're going to sit here a while and go, yeah, okay. That is my graph, right? It does fit somewhat in the scale here of things, right? We do have this coordinate here and this coordinate here, both at what? 0, 5, and 1 and -1 2/3. Those will probably be easy to see in this graph. We also have that horizontal asymptote at -5. That does appear to be happening down there at -5, right? And we do get that shape of exponential growth. The one point we're not going to see in this graph is this one way up here, because the top of the graph does stop at 10. Right? If we were to align a little bit more with what we have, we might adjust our window settings. Well, let's leave that at 10. But maybe we adjust this to be between -5 and 30 in value. Maybe we make that -10 and 30 in value, and we'll scale that by 5, right? Like we had scaled this by 5. What did I do wrong there? Oh, don't have a negative there, right? So there it comes. All right. So a little bit more representative of the scale here, right? We made a scale of 5 along this axis, and it goes from -10 up to to negative or up to positive 30, right, where we would see some of these key locations on our graph, as well as that horizontal asymptotic behavior on the right. All right, folks, so that is a couple more quick examples, and certainly all this work can be worked with your calculator, and I'm actually getting the ability to show you some of that with these examples here. All right, and all this is built upon transformations. This is nothing new. Hopefully you've spent the time with the transformations back in Chapter 2. This is the end of Chapter 2 material, 2.5, right? Where now we're just bringing it back into play here with exponential functions. And we're going to add to this, like I said, one more library function that we're going to add, and that is going to be the logarithmic function, where we're going to also have to use some transformations there, folks. So I will see you all then.